My name's Simon. I work for a company called SwiftStack. SwiftStack make object storage. Specifically, we make object storage based off OpenStack Swift, which to an extent anyway is something we also make with the lead contributors to the project on GitHub. I'm very grateful for being invited here today to talk to you briefly. About me, I work in professional services, and so my role usually is to go onto customer sites and try and help them to actually deploy this. As a result, we're going to try and start off at a relatively high level, and time permitting, there's only 20 minutes, get on some actual specific examples of how you could do this with Swift. So, what we've seen before, object storage and file sync and share tend to be a good fit. Unstructured data, you're dealing with high geographic distribution. There are a lot of users, so concurrency and scaling characteristics are important there. Infrastructure resilience, so if you're storing petabytes, well past terabytes of storage, you're going to need a lot of kit to do that. It is going to break. It's not a question of if. It's good if your storage system can react to that well. Durability, so every object stored tends to have high durability characteristics. What's perhaps more interesting is to be able to vary that as you see fit. And as with Swift, we have a feature called storage policies that allows you to decide how many replicas, what erasure coding strategy you want to use. And of course, this one's lifted straight out of the manual of one of the products we're going to look at later. The amount of data stored in product X will only ever increase. And that's very true. So, object storage then. These will probably be generally applicable to most object stores. They're designed specifically for unstructured data. You can't store a live VM, you can't store a database in them even if you want to. And the reason for that is because they drop semantics like file locking, like random access, seek. You can't do that with an object store. The reason that design decision is made is specifically to enable latency over long links, over geographic distribution. So if I put an object into Swift, by default, I'll get 3 replicas out. And those replicas will be written as uniquely as possible across the failure domains within my cluster. If I have to wait for both sides to sync up, then I'm introducing latency that is perhaps unwanted to my end user. And that is why we don't worry about file locking. We provide instead what we call eventual consistency. Eventually that last replica will get there. It may take some time. And dropping this requirement means that we can scale out across a single namespace over the world, and we can stay reasonably fast. In terms of hardware failure, in terms of concurrency, so again, got a lot of kit. Swift will rebalance your data. If a server dies, if the disk dies, then the data will go somewhere else to what we call a handoff partition. Briefly, when you resurrect your server, the data will rebalance back onto it. The data is highly durable. As we said on the last slide, we have storage policies, so you can vary the durability. If you have something that's very important, you can get your many 9s. If you have something that's perhaps a little bit less important, the cat pictures of the world, then you can reduce your durability to store those in a slightly more efficient manner. And again, in terms of expansion, Swift is shared nothing. The state, the location of the data coming into your cluster is known to every node. There's no database, there's nothing to index, there's nothing to worry. So in terms of growing it out, it's pretty easy. You just add more boxes as you want to continue. Okay, we need to talk briefly about it in order to understand some of the scaling stuff, some of the talking about provisioning later. But if you're running SwiftStack, you'll have a SwiftStack controller. This provides deployment provisioning, it provides monitoring. It wraps all of this up in a REST API that you can use to ease OpenStack Swift. Everything else here is pure OpenStack Swift. We don't modify it. We contribute to it as an open source project. We find it extremely useful to be able to do so. You have an access tier, so we support Swift natively. Obviously, we also support S3 for the use of a middleware called Swift 3. I don't really want to harp on about this. The access tier is interesting in that it is an access tier, but really it's the architecture underneath it that's important for any object store, because that's what gives you the scaling characteristics that you might want. So we run a variety of services. There's the proxy tier here that provides the access to our clients. You can tier this out separately from storage if you want to. Then we have some storage services in Swift. Everything is namespace into an account, which might be analogous to a user or an organization. We have a container, and finally we have the object itself. Consistency processes, which are necessary. If you write 3 replicas, then we send an OK back to the client on a quorum. Perhaps the last replica hasn't reached it. Perhaps you've got bit rot, perhaps your server's blown up. So we constantly audit the data, and we use replication processes to move it from our handoff partitions if something's gone wrong to where it should be. And finally, the point about hardware. So Swift obviously runs on commodity x86 Linux. I think the sites are there to indicate simply the way that failure domains work. So if you start off with 3 machines, say, in one data center, and then you add a second data center later, the failure domains will take account of that. So because it's shared nothing, as you add your boxes in, you're going to get more durability from your 2 DCs, but you don't actually have to make very much effort to make that scaling jump. So again, it grows nice and easily. Okay, so some file sync and share. We've done Swift in not too long, so hopefully we'll have time to get through the rest of this. Vendors on the right are proprietary. We'd like to talk about them because they have some bearing on the sides here. So Storage Made Easy are a company that we work a lot with. We've had a lot of tight engineering integration with them, and so as a result, they support quite a lot of extended features when paired with OpenStack Swift, legal hold and versioning and all that good stuff. The other interesting thing about Storage Made Easy is that when we see file sync and share deployments in the wild, we often find that they're SME with us. That's probably because of the integration. CenterStack is the rebranded name for Gladinet. That one's of personal interest to me because a couple of years back I spent about a year on a client's site. Their use case was file sync and share using it. We're going to see one of their architectures later. As we scale out, they'll be one of the examples, and so that's one of them on the slide. Then we have, of course, OwnCloud, Nextcloud. So OwnCloud is there largely because of its popularity. We've done some integration work with them in our lab, so we're going to talk about them briefly later. If you talk about OwnCloud, you also have to talk about Nextcloud because they are their fork. They're currently gaining a lot of traction on GitHub. You should probably consider one a drop-in replacement for the other. So although we're going to talk about OwnCloud, Nextcloud is also applicable. And of course, there's Cfile, who are another popular product. They're gaining traction in academic institutions at the moment. We'll talk about them briefly, hopefully, if we have time. So integration points. In terms of integrating anything, you need to work out where they touch. And in terms of file sync and share and an object store, obviously the primary function of the object store is to provide storage to the file sync and share. We've gone on this point before. It's great to be able to scale the capacities we need. We don't want to provision 10 petabytes if all we need at the start of 300 terabytes. The second point is slightly more interesting, perhaps, provisioning space for users. As it turns out, when you link up a file sync and share solution to something like OpenStack Swift, how you provision it becomes quite important, because the primary reason for getting an object store, or at least one of them, is to scale it out. If you do this wrong, you're going to hurt your ability to scale it later, so don't do it wrong. And there's a kind of wish list item at the end behind me. Dual access. It's quite nice to be able to put data into our sync and share, and then perhaps be able to reach in and grab it from another client that speaks Swift, that speaks S3, so we can do more with the data later. You don't always get this option, but if you can, it's nice to have. Okay, first topic, scaling. So scaling with Swift is fairly easy, as we said. You add more hardware. There's no shared state, that's about it. So the question becomes more, how much do I scale by? Do I want to scale by a box at a time? Is it more efficient for me in terms of the way my data center is laid out to scale by the rack instead? This will affect your tiering decisions. We'll see that later. If you scale by a box, you probably want to run all of the Swift services on one machine, which is what we call a PACO, proxy account container object. On the other hand, if you want to scale by a rack, you suddenly have more tiering options available to you that might become interesting. Account and container storage is more of an implementation node. So in Swift, data is stored, objects are stored specifically as data on an XFS file system, and that's where our attributes go as well. Accounts and containers are SQLite databases, and if you back them on a hard drive, then although there is no theoretical limit, there is in fact a practical limit at which things are going to start to slow down. If we pump 1 million objects into a container stored on a hard drive, then we may start seeing some performance problems. On the other hand, if we store it on an SSD, we can go up to more like 10 million. So use SSDs because they're not 10 times more expensive. The final point is something that's personal to me, load balancing. The last 3 major deployments I've been to, 2 of them had problems with bottlenecks, and both of those were caused by the load balancer. When you put Swift in, it is very tempting, because it's a web service, to think about slapping a load balancer in front of it and thinking, great, I can now distribute my load. We'd suggest that you think very carefully before doing that, because if you do, you'll find things like your SSL throughput. If you're running a HA proxy, things like ephemeral port ranges might come back and bite you. We actually suggest you don't use a load balancer at all. for something which is erroneously entitled the Swift Stack Load Balancer, in which we put VIPs, all of our proxy accessed here, we fail them over using VRRP if necessary, and then we just put a nice round-robin DNS on the top. So here's an actual customer example. These guys wanted to scale it by the box. They're running all the services within each node as a PACO. Two networks here. So we have an outwards-facing network. That's where the clients come into the proxies. We have a cluster-facing network. Both of these need to be very fast. That's probably all you need to know. And to scale it, nice and easy. Next example. This one was the GladNet customer that I referred to earlier. So these guys wanted to tear out their proxy separately to their storage. I'm not sure that I'm convinced by the arguments as to whether this is better than the other particularly. If you have a proxy doing nothing on a box, it's doing what a web server does. It sits there running the accept system call a lot. It's probably not causing you that many efficiencies, but you might prefer it for other reasons. And so these guys set these up like this. As you can see, there are a couple more networks here. It's a bigger install. There's a controller network. There's an out-of-band. Both of these don't need to be fast, so we haven't bothered with 10 gig for these. Not shown here is another data center. They had 2 DCs. That means there's also a replication network. If you have a replication network for your object store, make sure it's fast. To scale this then, very easy. Only one thing about this slide. This shows 1 proxy to 3 storage nodes. They had a ratio of 1 to 4. The proxy nodes are pizza boxes. The object nodes were probably 3 or 4U. Okay, our second topic about integration then, so provisioning. There's a lot of bullet points here. There's really only 3 points to make. So the first one is, hopefully, your organization has a single source of truth for your users. If you do, it's probably an LDAP of some sort. It might be Active Directory, it might be an open LDAP. Every product that we've seen so far, including Swift, supports LDAP as an integration for users. So the simplest point of adding a user in is probably to turn on account auto-provisioning in Swift, and then to apply quota on the sync and share. The second point is more about dispersion of your objects. So as we've seen before, the namespacing works that an account, a container, and an object. You might have performance problems if you don't disperse your data properly. Equally, you're going to have problems with ACLs. In Swift, every account is by default delineated from other accounts in terms of permissions. If your sync and share doesn't map to that, and many of them don't, then you're going to have to worry about ACLs later, which can make your life more difficult. And the final point is, of course, the dual access. If we can get it, it would be great to be able to access our files from outside of the sync and share later. First example. So, OwnCloud. This is based off some work that we've done in our lab. If you provision with OwnCloud, then you'll find that there are 2 types of storage. There is primary storage, which appears when you first configure it. Primary storage, sadly, is not ideal for our purposes because it does 2 things we don't really like. The first one is it shoves everything into a single container in Swift into one account, which means that everyone's data is going in there. That's probably not going to scale out later. A second problem, although not such a big one, the objects are renamed into a URN naming scheme that it uses internally, so we can't access them outside. However, there is some good news, which is that OwnCloud supports external storage. External storage is a feature that allows you to mount other storage. OwnCloud's mission statement is pretty much to get all of your data, no matter where it is, and funnel it all the way through OwnCloud. So it's pretty much a first-class citizen. It's reflected in their CLI, it's in the API, it's good to use. And so if we use it for Swift, it turns out it actually works really well. We can connect an external storage area up to any account, any container. As a result, we get all this nice scaling. We're introducing no bottleneck. We can also do some dual access. The files within there are not renamed, so we can access them from another client. The other nice thing about this is that because we can point to different containers within Swift, we can now use storage policies. So we can tier our cat pictures differently to our actually important data. Example, sorry about the text size. I'm not expecting to remember a load of JSON, but the point here is, I guess, that this is actually relatively easy to sort out in an admittedly somewhat sugar-coated environment. Add the users to the LDAP group. That will give them access to your Swift cluster, hopefully to your own cloud as well. Then we put in a container into Swift. This is a HTTP put. Then we use the OCC CLI in this case to add our own cloud account. We give it an endpoint in Swift. We give it the own cloud user it belongs to. Then finally, we use curl to set a quota using the OwnCloud API. I'm going to talk briefly about cfile. I think I might be running out of time. So cfile does not have a concept of external storage. It has one storage area, and again, a similar problem. At most, we're going to have 3 containers being used. So there is an interesting thing about the way that cfile names objects. It names them using UUIDs. And this is good for our purposes because you can use in Swift a middleware called AutoShadow, which we make. And the reason we make it is precisely to solve this problem. If an object is named with 3 preceding hex characters, we'll create a container for it automatically. We'll create several of them. And we'll present a virtual container back to the user to make sure that things scale out nicely. There is an example here, but I'm going to skip it. You can download the slides later and then look at it later. So then, technology like Swift is designed to throw quite a lot of things out the window. And the reason it does that is in order to try to be very good at other things. That means that your use case is very important. Some use cases will allow you to leverage the advantages without suffering from the downsides of doing this. We think that file sync and share is one of these. The second point is something from my hat as professional services. Because the main reason you use an object store is to do with scaling, make sure that you choose deployment and provisioning strategies that don't impact your ability to do that. There are some links here. One of them that's more interesting perhaps is our OwnCloud integration document. But in the meantime, thank you very much.
Questions for Simon? While it resumes, you mentioned the adding SSDs at a certain point. Do you have some rule? Do you have some rule of thumb in terms of how much, which is the ratio? I mean, how do you scale a system in those cases?
On an object node, I think 2 SSDs are generally enough. Like if you're taking, say, a 3 box, if you've got 36 disks, we probably recommend about 2 SSDs. I'm afraid I can't remember the exact ratio we recommend, but there are some things online that will give you a ratio for that. Yeah, about 2 SSDs are what we should do it. Yeah.
So clearly there is also, let's say this object storage world is now being kind of split between Swift and Ceph.
Yes.
Why would I use Swift, not Ceph, or why would I use Ceph, not Swift?
Yeah, the Ceph question is an interesting one. So Ceph doesn't give up the locking. I think that's generally the answer that people like me give when asked this question. Ceph is brilliant for block, but it's not eventually consistent. You might think that's great. You might think it's bad. If you take eventual consistency, the purpose of it is specifically to enable you to keep giving decent latency to people when you go over WAN links. But there's a massive downside, which is suddenly you're eventually consistent. What that means in practice is you put an object in. If you then retrieve it, you'll get the same thing. But if you modify that object and someone then immediately attempts to read it, they might get the latest, they might not. So you gain in terms of being WAN links, but there's a loss, there's a downside as well, and that's the difference. Whether you want to take that difference is very much up to you.